this rather boring thing here. I can maybe introduce myself. So, hi, my name is Armin Ronacher, and I do a lot of open source. And I'm very grateful that over the last 8 years I was able to do open source in a commercial context, working for Sentry, which is, I would argue, an open source company. But I will admit that there is some controversy about how open source we still are, because we are also a commercial product. And so I don't want to talk too much about what it is that we're doing, but I did want to give a talk that covers interesting things that I personally find exciting, and I spent 8 years working on this, so I like to talk about the stuff that we built there. So, as mentioned, I do a lot of open source. Most of it out of the Python ecosystem, and Sentry is built in Python for the most part, so this is where I come from. But I also have a lot of interest in other programming languages, and I introduced Rust a couple of years ago at Sentry, and so there's a growing ecosystem of Rust code appearing there, and it will find its way into this presentation a little bit. This is a little bit more of a technical talk, and I know that a single-track conference is a sort of a hit and miss if it works. But I think it's quite interesting of what we do, and some of the lessons that I've learned, and I think many of us have learned, taking something that is very small, a very small open source project, and scaling it up to the size of the company it is today. So if you've never used Sentry, I just want to show some screenshots so you can connect the talk to the user experience, because it makes a lot more sense if you understand what the idea is. You can think of it this way. There's an SDK. You can implement it in your application. It monitors when something goes wrong and says a crash report or an error report to our service. So our primary job is to take the error report, to process it into something that's human readable, maybe send you alerts, maybe do a bunch of other stuff with it, and show it to you, or alert you, or count how many times did it happen. There's a bunch of other stuff too, like you have a session replay where you can watch someone sort of click around in a website without PI. There's a tracing product where you can see interactions that are happening, for instance, HTTP requests going out. There's a profiling product connected to it. There's a lot of stuff going in, and the sum of it is more scale than I've ever worked on before. So in terms of getting all this data in and showing up within milliseconds to a customer is an interesting problem. So what I will not talk about is any of the operations part, any of the infrastructure part, any of the how you get a company going and actually not beat each other up and make it build a coherent product. I'm also not planning on talking too much of development processes on it, but we documented some of it if people are interested on the development docs. I want to give you a little bit of a sense of scale on this. This is not entirely up to date, but in terms of what data goes into the system, we're talking about around, depending on where you measure and what you measure, around 300,000 requests a second that needs to be dealt with by the ingestion system. And so this is the primary point of what we have to work with and what we have to make sure that works. And this is not little analytics events. Those are, some of these events can be hundreds of megabytes of crash dumps, or it can be this very bursty session information, like someone just started the session. It can be a whole bunch of this. And so this is sort of the scope of what we're trying to solve. As mentioned, we're an open source product, and this means in certain ways that it puts some limitations on you. The asterisk part is that I consider Sentry to be 90% open source and 10% what we call eventually open source, which means that it's Apache 2 licensed, but the most recent, I don't know, it's right now maybe 3 years of rolling license has a restriction on it that you can't use it for a competing product. But if you take the code from 3 years ago, it's fully open source. Okay, but the open source part matters not just because I like open source, it also matters because of the technologies that we choose. So even the commercial offering of Sentry runs fully on open source software. There's a little bit of proprietary cloud stuff in it, but mostly just so because we found it to be cheaper in certain cases, but we never run it in a way where we make ourselves dependent on some proprietary technology. It's always within 90 days it should be possible to switch off. Technology-wise, these are the languages that we chose. I would say over the last 5 years, I had to answer a lot of questions about why we chose those languages. And to be honest, a lot of the reasons why we do anything at the company is not because we thought deep and hard about it. We did something, it worked, we kept doing it. This is how we ended up with Python. This is how we ended up with TypeScript. This is how we ended up with Rust. Wasn't bad enough to switch off, and people like those languages for the most part that are working on it. The database of choice for us is Postgres, ClickHouse, and Redis. Very boring databases, I think. There's like nothing fundamentally tricky about it. But if in the context of what's going to come, it's like all open source technology. And getting 300,000 events through a pipeline requires some form of queuing system, or where we're using Kafka and RabbitMQ. Okay, and the last important part to get us off is like, what is it that I'm talking about? The most interesting bits and pieces of Sentry infrastructure is Relay. That's the system that takes in all this traffic, that deals with all of it. And I think this is where you can take the most lessons out of the whole part. Then there's a Sentry monolith. This is a lot of particularly old Python code. It's split into the Sentry component, which is sort of the open source code you can download on GitHub. You will find everything in there. And then there's a tiny, tiny bit of hidden code, which primarily deals with compliance, credit card transactions, and stuff like this. Front end is all written in TypeScript. And then we have some internal systems like Snuba, which is written in Python, which is querying ClickHouse, and Symbolicator, which is written in Rust, which deals with converting memory addresses into human-readable function names. And one of the things you will notice is that there are actually not that many of them, because we're not strong believers in microservices, not because we don't like them. Actually, I think they're better than their reputation. But it's actually surprisingly hard to get everything running on a local computer, on a local developer's machine. And again, being an open source project, we want to make it so that any person in the world can actually make this thing run. And there was a really strong wish not to, I don't know, spawn Kubernetes on developer machines. So we're relatively constrained to how we pick this. And I think this is actually something that I really quite appreciate that we have accomplished. Okay, so what's an event? When you build a system like this, and I know there will not be that many people that probably build an error monitoring system, but what's to take away from it is that you will probably in your work at one point or another have to deal with similar types of problem, which is someone sends you a lot of stuff and you need to work with it and you need to produce results as quickly as possible, and you need to deal with every kind of problem that the queue gives you. And the types of events that we are dealing with is primarily errors. So error reports, they require some processing. Trace data, which is sort of distributed tracing data that you can look at. Attachments, which is basically binary data that can come in very small to very large. Crash dumps, which are incredibly hard to process at scale. And then we have to deal with a whole bunch of stuff that we have no control over. Most of it comes from our SDKs, which is awesome because then we have full control over the whole experience, at least in theory. Third-party stuff is a whole different story because we are restricted by whatever they are doing. And that limits you what you can do. And actually you have to build way more resilient when you build something that has to integrate into an ingestion system that is not driven by you. And lastly, they have client reports. And I will talk about this in a little bit because I think that this is an interesting concept that we have come up with. So where do these events come from? Most of them come from SDKs. So think of it this way. It's a piece of code that someone embeds into an application, and it does something. It monitors, it keeps just paying attention to what's going on, and if it finds something worthwhile to submit to the central service, it will do so. Most of the original code came from Python, so you would monitor your Python web backend application. But the more interesting one was always browser JavaScript. So if you have a front-end application in JavaScript, it will minify. You will have this sort of very small bundle of JavaScript that's being produced, and then you want to monitor it. And so we have a little SDK that sits in there that looks when an error happens, and it sends this minified stack trace to you, where like every function name is just a single letter. And what we have to do is we have to like process it up with the original source maps into this original human-readable stack trace. And what makes this interesting at scale is that if you have not just one project to do this with, but you have like hundreds of thousands of projects of doing this with, the total amount of data that you have to work with is really quite challenging, because if there are like 120,000 projects sending you JavaScript errors at the same time, you need to keep 120,000 worth of source maps and all this data around to actually make this to process this. And then there are obviously other people building SDKs. But the last part is this nested relay infrastructure. And this is, I think, an interesting system that I haven't seen outside of our company used much. But I think it has quite interesting benefits. And I think there might be more out there that build a system like this. And I will go into this a bit. So where do these events go when they go into the system? And so this is, I think, this is where relay comes in for the first time. What is interesting about like how we designed this, or how the ingestion system works, is that when we were very small and we had a very, very small open source application, the path of an event into the system was pretty straightforward. With an HTTP endpoint, it got a bunch of JSON, it literally threw it into the database. Right? That gets you that far. Eventually, you realize that writing it into the database actually takes a bit of time, and it scales a little bit different than scaling up the web worker. So the first thing you do is you put a queue in there. Event comes into an HTTP endpoint, you take the JSON out, you put it into RabbitMQ, and then you have another worker that picks it up and eventually throws it into the database. That works really well, and that got us over many of the years. But at one point, the cost of an event actually scales really badly to you. Because if you have 120,000 different projects that require processing at the same time, it means that for every single event that you pull out of the whole thing, you need to load the state that's necessary to process this event. And then after you have done the event, you're done with it. So one of the biggest challenges with building a system like this is actually dealing with the data they don't want to have. Like if a customer churned, if they no longer pay for something and they keep sending you the data, you don't want to have to absorb all the cost the customer gives you. You have to really quickly turn it off, right? So you have to know which customer is no longer a customer in a very fast time. And so the way this works in our system is we have this relay infrastructure, which is ingestion points that are very, very stateful. They know a lot about how the system works, and they're all over the world. And that means that they have a communication going on to Sentry to figure out, okay, what data do I need to very quickly decide what's the minimum set of processing I need to do on this event to decide if I want to keep it or if I want to throw it away. And if I want to keep it, I have sort of two outcomes. I want to keep the whole thing and send it onward, or I just want to accumulate the counts. I want to see like how often did it happen. And then we have this communication also going to the Sentry SDKs. If an SDK is being informed that, well, actually you're way over quota, you're sending way too much stuff, I want to be able to throttle the SDK. Because one of the interesting challenges is mobile applications. You might have a very small developer that builds Flappy Bird. It's an app that maybe has our instrumentation in it. And that app is free. It doesn't make any money, right? There is no reason for that developer to spend a lot of money on us. But every one of their customers sends us crash reports, right? And so it can be that a very small developer that only pays us $29 a month creates a server bill that's multiple magnitudes of this. So we have to find a way to make these accounts cheaper. I will fully skip over this. This is very boring, but it gives you a little bit of an insight of like what happens. The first part I was showing you is literally just the thing on top. The rest is a whole bunch of like internal where do I route the data. It goes to Snuva, which is our query service for ClickHouse. We store a bunch of stuff in Postgres. We store a bunch of stuff in at the moment Google Bigtable, but we just use the key value store. It basically goes in different places, right? And so what we are trying to do, and this is, I think, what I had most enjoyment with over the last couple of years to build, is find a very efficient way to route the right data to the right place with the least amount of work necessary by avoiding building new problems along the way. Because what you don't want is to wake up in the middle of the night and be told that you have a downtime now. So the goal is to reduce the total amount of time something goes wrong. So what are these challenges? The first one is point of presence. I think that once you have reached a certain size as a company, you realize that not every customer sits in the United States. We have an engineering office in Vienna, which is primarily responsible for ingestion part. We have an office in San Francisco, which is more on the data storage side of things. And so we were always distributed from the start, but it took us a couple of years to actually build points of presence, because it's actually not an easy problem. Points of presence means I don't just have all my infrastructure in the US, I have a bunch of infrastructure over here, I have a bunch of infrastructure in Asia, and the goal is to minimize the latency that my customer's customer has to our ingestion point. So if you have a PHP application, this is the bane of my existence, one of the biggest problems is that when it makes an HTTP request, it doesn't do it async. Like you slow down the application until it's sent to us, right? So to make PHP people happy, I need to be very quick at getting the event in. There has to be like really quick response time. So I need to get my infrastructure as close as possible to my customer. And for some applications, I want to be able to bring my infrastructure into their Docker container, right? I can bring my infrastructure right there to this PHP thing. And so that's what we're trying to build. And so this is this customer-side relay where it's like not just can I bring the infrastructure to Frankfurt, Germany, I can then tell a customer to say like, take this little piece and put it into your Kubernetes infrastructure, and then this is the latency that's of concern for you. One of the interesting challenges is this churned mobile app problem. This is sort of what I related to earlier with you have a small customer that maybe pays you $29 or maybe doesn't stops you paying, but they still have the SDK in the mobile app. It still keeps crashing, still keeps sending you stuff. So you need to find a way to make that cheap. Misshaped customers is the same thing. It's a customer sends you very little data, but actually exhausts all your bandwidth. This is hilariously common, especially with free trials. Like someone puts this in, maximum sample rate, doesn't care. All of a sudden, like all your traffic is, I mean, at our scale, it's no longer the problem. But like for a really long time, you had this enterprise customer trying something for no money or very little spent because like a random engineer just put a credit card in somewhere. You have to figure out a way to make this work cost efficient. And so that's why we put a lot of this logic into the points of presence. We want to process as much as possible very close to the customer so that we also throw away a lot of data before we pay for the network egress to the rest of our infrastructure. So we need to get as much of this config as possible into this points of presence. And then my favorite of all problems is just that it's very easy, I would say now from experience, to build a product that has all the same events. If all you do is count how many times did an application start, how many times did an application end, every event looks more or less the same, I can build this at scale. I've learned this now. I still don't perfectly know how to build something where an event that looks exactly like the other event takes 5 minutes to process versus 1 millisecond. This multi-order of magnitude scaling problem that we have is really, really annoying because I can't tell you ahead of time how long it's going to take me to process your crash report. Why is that the case? Because I need so much extra data to process these crash reports, and I might not have the data yet, and I might have to fetch this data from a really, really, really slow FTP server somewhere. So this is a very complicated problem because I cannot tell ahead of time how long it's going to take me. Okay. Pipeline extends to the client is how I would describe our system. The idea is roughly this. There's a processing pipeline that exists somewhere. It has Kafka, it has RabbitMQ, it has all this sort of stuff, and eventually it sort of goes to relay, and there's a bunch of stuff in there. But our processing pipeline really wants to control all the stuff on the client too. So there's a little bit of pipeline, event processing pipeline embedded right in the SDK. So I'll give you a very pragmatic example of how this looks like. If I ever built a React Native application, there's JavaScript in there. But there's not just JavaScript in there, there's also Objective-C code in there, right? So there's an SDK that captures errors in JavaScript. It knows really well how to do that. But then there's an underlying system that's written in Objective-C, and it has some extra data that's really valuable to send along, like for instance, what's your battery charge? How loaded is your whatever, like your CPU? Maybe there's some device metrics I want to send along, right? So there's an underlying SDK that's our Objective-C SDK that we also want to send data to. So basically the way this works is JavaScript SDK comes up with this really cool crash report that looks really nice from its perspective. It sends it one layer down to the native SDK, which adds its kind of data on it, and then it might send this onwards. In some cases it gets very absurd, because if you have built a React Native app using NDK on Java, you might have Java, C++, and JavaScript in there. And so we basically treat the client-side experience as if it was under the same rules and responsibilities of the server-side pipeline experience. So that's the idea. It's like our processing pipeline has some life on the client and has some life on our infrastructure where we can see it. And managing the pipeline that we don't see is interesting. The way we do this is we didn't come up with this. I think someone else did, but we basically defined this concept called an envelope. An envelope is a basic container around stuff. It's primarily a container around our primary crash. So if you have a crash JSON thing coming in, it's interesting to just put this into an envelope, and all the envelope does, it says like, there's a crash in there, and it's JSON. It doesn't really do more than that. It's just like, it's basically a way to serialize an arbitrary thing, and it tells me what the thing is. And I can put multiple of those things in. Why is it valuable? Because, for instance, if the JavaScript React Native SDK now comes up with this great idea that it wants to send performance profiles, and the Java SDK underneath has no clue what the performance profiles are, it doesn't matter because it puts a new performance profile item into this envelope, puts the envelope into a queue that goes to the native SDK, which has like, okay, I know what a crash report is. I could do something with it. I've never seen this profile thing, so I'm just going to ignore it and send it onwards as if I don't know anything about it. So I'm going to lose some of the benefit of it, but it basically means that I can chain these things together. And anything in between that is unaware of what this new kind of thing looks like will just transparently forward it. This is really hard to solve if you don't abstract over it properly, because otherwise I end up in a situation where I have, every time I build a new feature, I have to figure out if every consumer is capable of dealing with this thing. Because, for instance, I already mentioned earlier, if this is PHP customer in Frankfurt, Germany, that really wants even less latency to this thing and runs a local Sentry relay, if they don't keep updating this relay all the time, they might have a relay that doesn't know anything about profiles yet, right? And so I don't want to say like, hey, customer, you have to update your relay to capture profile data, because really there's no reason they have to update it, because we don't do much with profile data in relay. So it's basically, this idea is we abstract about what kind of data comes in. And so in some cases, we upgrade stuff into an envelope. So for instance, if you have a CSP report, which is, I don't know if you're familiar with it, this is basically a browser-issued report about a security violation, that comes in its own format that browser vendors come up with. What we do in a relay is we take the CSP report, we put it into an envelope, and the next relay in line will get this envelope. And we keep sending this envelope onwards. The envelopes allow us to put any kind of data in it. So if you want to send binary data in it, you can say like, hey, the next thing is a 200 bytes worth of binary, and then it's just in there, and then there's more JSON again. So it's basically just, you can think of it almost like a multi-part email, where you can add multiple different bits and pieces, just that it's a lot easier to parse than MIME data. And each of those envelope items has a specific data category on it. And this is really important for the rate limiting part. Because what relays do, first and foremost, is enforce rate limits. If I have a customer that only pays me $29 a month, I better not spend more than $29 a month in infrastructure cost on that person. It's not entirely enforceable, but it's better than having this sort of thing balloon out of proportion. And the way I can do this is I really have to get rid of the network traffic. And so if I, for instance, see like that customer can send me 1,000 events, but they're actually blasting me with 10 billion events, what I really want to tell the SDKs is like, shut up. Like, just don't send any more stuff. And so we communicate these, what we call reset windows, back to the client, which is basically at which point are you allowed to send again. Usually we tell you to stop sending for a minute, or maybe in extreme cases for an hour. For some of the data that we don't want to forward, because we really want to keep network traffic down, is we do a bunch of like extracting in the relay infrastructure. And so, for instance, if you send a bunch of crash reports, right now every one of them will make it to Sentry. But for instance, for performance profile data, only a fraction, let's say 1% of the profiles that you send to us will actually land in the system. Most of them are just going to be aggregates. And so really keeps the counts with some dimensionality, but we'll throw away the rest. Okay, so how do you communicate quotas? This, I think, is something that only developed over the years, essentially a better understanding of how this can work. But I think we're quite happy with how this worked out. And I think it's a really good pattern that I want to take to more places, because we basically say like the envelope is the carrier of data. So you can put anything in there, but I can discard individual items out of it. So for instance, if you still pay me for performance data, but you're out of budget for errors, I can tell the client to no longer send errors, but it will still send performance data. So I can regulate what can still send. Maybe you have only a budget of like so many terabytes of attachments a month, so I can tell you, please don't send any more attachments anymore. It's not worthwhile. So you can reduce the total amount of stuff that goes to the network. One of the things you can always send is client reports. And this actually we only built really recently because we didn't really understand how a system works. So as I mentioned, the pipeline extends to the client, which means there's stuff happening on client devices. I have no control over them. I can build an SDK, I can hope that the customer eventually updates the SDK, but I can't force a customer to update the SDK. I can't force the customer to roll out something with debugging in it. Like I have no visibility in it. And particularly, I don't see it in the process of all of the events that I see in the system. And so client reports, we added just to see what's going on the clients. Like how often does a client not send? And so this is a graph from like the internal debug stuff. But basically, purple means we accepted everything. Yellow means the client threw it away. And in a normal situation, you really would expect that the client doesn't ever send anything away because everybody is well within the budget of what they want to pay for. But it turns out when a customer has really, really spiky services, in some cases, the client can't even send it on the network because they're internally saturated, right? And so if you don't have a way to see what's going on in the client, you will never observe this, right? And so the idea is that we count on the client how often they did not manage to send something out, and of what type of data they did not manage to send out. And then we can send that data out, which hopefully makes it through, because we always permit this kind of data to flow through to see what's going on, right? And so if you now look at this particular customer in May 17th, if they reach out to customer support and say like, hey, where's my data? Someone from support can say like, well, your data is partially not there because, for instance, your network was down, or you just had an internal overflow, like it was just too much stuff. So we will see that. And this is actually really important, because if you build a system that's all about throwing away data, not seeing the data that you throw away can really throw you off course. So for instance, this on the right, this is a customer that had one day where they rolled out a really, really shitty deploy, and it was crashing so hard that the SDK didn't catch up with sending the data out, right? And so multiple orders of magnitude of non-data was just dropped on their side. And without these reports, you would never know, right? Because we wouldn't attempt of sending this. We would never see it on our infrastructure. But because we sort of overlay like all these outcomes from everywhere in the system, including all the data that we lose on the client side, we have a little bit of a better visibility. And it took us 5 years to come up with this, because we didn't think that the problem is that big. And then once we started measuring, we realized that, holy shit, the SDKs actually have a whole bunch of really bizarre edge cases where they lose a lot of data. And so this way we can see this. One of the earliest lessons that I've learned at Sentry is that if you tell people to shut up for a minute and they all come back on the minute, you DDoSed yourself, right? You don't want to tell every customer to come back exactly on the hour. You don't want to have the customer come back on every minute. So we jitter everything out. Our traffic looks incredibly well with this sort of pattern. And if I take out this code, we have a multi-hour downtime because I wouldn't recover from the amount of pressure coming in from millions of devices trying to hit me. It's impressive how good clock synchronization is. That's all I will say. Another thing is like, there are these misshaped customers, right? And in our case, it's very clear because like every customer is like very, very specific. We can look at them, we can talk to them like they're humans, and they themselves have customers, and we can't talk to them, but we can see the data that they produce. And so it's easy enough to talk to them, to engage with them if they're doing something really problematic. Because it actually turns out that it's not that hard to misbehave on data egress in a way that is very, very painful for everybody. I can craft you HTTP requests where the Sentry system will go into a degraded mode, and we'll have to say like, well, this customer is doing something really, really stupid. Very simple example, if I send a JavaScript event with source maps, and the source map, I don't know if you're familiar with it, but it's basically a huge JSON file that says like, this line was originally called this function name, right? It's like, take a small thing to a long thing. This file is fetched via HTTP. If I'm really, really malicious, I host this source map on a very, very, very slow HTTP server. Like that takes 15 seconds to respond with the source map. And then I send a couple of thousand events in, right? And Sentry's infrastructure is going to go to a really slow HTTP server and try to get really hard the source map to do something. And eventually, if you do this long enough, you're eventually going to exhaust a whole bunch of resources, because under normal circumstances, that doesn't happen, right? And so I have to find a way to detect this behavior and turn it off, because it's usually just one customer doing something. And it's not even maliciously intended. It's just that the customer did something, and maybe they're not even aware of what's going on, right? And one of the interesting challenges here is that I originally thought that the goal is to process every event. And it turns out it's a really stupid idea. The goal is to tell someone when they're in a window that you can no longer service. Because you can think of the whole thing like a bathtub. Under normal circumstances, the water that comes in and the water that flows out is more or less like the outflow is bigger than the inflow. That's what you want. If the outflow is less quick than the inflow, then eventually you're going to run over. And there's no point in building bigger and bigger bathtubs, because the core problem is that it actually increases in size. Like there's more stuff coming in. And so the reason it can be quite painful to work on an event processing system is if you have that many events coming in per second, and you just press pause for a minute, you have a minute worth of those events coming in a backlog, right? They're sitting there. Your bathtub is filling up. And maybe that keeps going on for like 15 minutes. And eventually you're going to press the continue button, and you're going to work on the oldest events coming in, right? So you're going to go from the data that came in 15 minutes ago. And eventually maybe you have enough infrastructure in place to catch up with everything. But that means that you inherently extend your downtime, because even the events that are coming in now, they're just at the end of the queue. They're waiting, right? So you have to burn through this backlog. So you really don't want this backlog to begin with. And so the best way to do this is to be very honest about it. It's like, we rather throw a bunch of stuff on the floor right now, Mr. Customer, and please like reconfigure your server to be faster. Then it will no longer happen. Because if I don't tell the customer, they have no reason to make the server faster, right? I'm committing myself to always hitting this 15-second server to download the source map. They don't even know that something is wrong, right? So we have learned a little bit about this. It's like you have to bring the customer into this equation. For how we communicate the state from like what we need, like there's always a place in Sentry that has all the data that is relevant for processing. But that has to make it all the way to the relays, and in some cases the quotas have to make its way over to SDKs. We've learned a bunch how to make this more efficient. The way we're doing this now, and this is also years of experimentation, I think, in some way, and in retrospective it all seems very, very obvious, right? But you don't start it this way. You start with something simple, it works, and eventually, over time, you realize it really scales really badly, and then you realize that that is actually unnecessarily complicated. The way it used to work is relay makes an HTTP request to Sentry, or another relay, and it will get config update. And it actually turns out that if you spawn a new relay that has never seen anything and you put it into the load balancer, it's going to take it only about 5 minutes to hit residential, have seen every project. Right? It's like the graph, I don't have a picture unfortunately, but like the graph in the monitoring system is basically no project state loaded every config within 5 minutes. Right? It's very quick to get everything. And so we eventually figured out like that actually means great cache utilization. Why do we not just read directly from the same caches that Sentry has, right? And so we went from like tens of thousands of HTTP requests from relay to Sentry to basically 0, because it just reads the same cache. It's like, why did we not do this originally? It's just, it didn't come to our minds that you could do that, because it sounds really dirty. It's like the system over there has the same cache as this completely unrelated system over there. Why would you do that? It's like violation of like separation, but it's like good violation of separation. It's mind-boggling how much more efficient the system is now. This is, as mentioned earlier, one of the biggest problems is like if you have multiple orders of magnitude of complexity of one event to another event, it's very hard to figure out what you're going to do with it. Now, it looks very obvious that the small event payload is going to be faster than a large event payload, and that you know ahead of time, so you could say like, okay, I'm sort the small things and the big things into separate things. That seems intuitively obvious. But how long something is going to take to process actually is completely non-obvious. It's a very good example, user agent headers. I don't know if you're familiar with them, but it's basically like a huge list of ways in which browsers identify themselves. And there's a system called user agent parser. I don't know if you know that, but it's basically 10 megabytes worth of regular expressions, right? And you basically parse them all, and you try to see, is it Firefox? That's basically it. Is it Firefox? Is it Chrome? Is it Safari? What version is it? And depending on this string, you're going to be either by one of the first regular expressions to hit or one of the larger ones, like inherently or of whatever. Like it's probably n squared or something. I don't know what it is, but it's like it scales really badly if you consider what it does. And so you really don't know ahead of time necessarily which stupid path it's going to take. And even an innocent small event can, even if you already know it's never going to require complex processing like source maps, can still take longer or shorter. But the really big problem is once you talk to the ugly external world. Like if I have to fetch source maps, I'm already really sad. But I don't know ahead of time because there's a lot of caching going on. And maybe I'm super lucky and I hit the cache. And so the same event cached can take milliseconds, or it can take 2 minutes because I'm fetching so many source maps from a really slow server, right? And it's very hard for me to know this ahead of time what's going to happen, which means I don't really have a good way to prioritize any of this stuff. So I mentioned this earlier, queues can balloon. This is really annoying because it means that if I accumulate all this backlog, I commit myself to having to do this work. And emotionally, it was very hard for us to get into this idea that you better sometimes not do some work and just willingly throw everything on the floor and just say, this is better for the overall health of all of us if we don't do any work here. And so we are very specific now in detecting shit's wrong. If the symbol server that we're going to fetch a bunch of PDBs from or dwarf files or any of these huge debug files, we will put you on a naughty list and will not hit you. The same thing with source maps. We give it very tight requirements on when it has to come back. If it doesn't come back, scale up your server, right? That's sort of the idea. And so you bring the customer into this conversation, because if I don't show the customer, like, your database server is slow, they have no incentive to scale up, right? But if I tell them, then maybe we can all work together and get a better experience out of this. The other problem is that it's really, really hard to scale queues. There's a lot of theory written about how you actually scale this, but if you build a system like us and it has organically grown over the years, you have only learned about backpressure management 5 years in, so you have built a system that has insufficient backpressure. And what this means is that sometimes the system really only works because it doesn't work too fast. And so you can think of it this way, there's a bit here that produces events, to the next thing that produces events, to the next thing that produces events. Inflow in the beginning is a certain number of events per second, outflow at the end is a certain number of events a second. Let's put the pause not at the beginning, let's pause it somewhere in the middle. And so now this queues up, right? You have this huge queue of backlog. But the thing here is really fast at consuming. It's like blazingly fast. So you press continue, it produces, and the next thing falls over, because it doesn't have the capability to deal with this many things coming in. And so having this sort of backpressure management throughout queuing systems, if you haven't built it in the beginning, it's really hard to retrofit. And, well, we only learned on the job. So we have learned over the years it's really great to put Kafka in between things, because Kafka, like RabbitMQ, which we have in a lot of places, if you put a lot of stuff into it, it falls over. Kafka doesn't. It puts a lot of stuff on disk. It's perfect. The only problem is Kafka has head-of-line blocking. I don't know how many people are familiar with this idea, but basically Kafka is like a queue. It's not a queue, it's a streaming thing, and it has a bunch of partitions. And you put an event on a particular partition, and then one event after another one and after another. So within one partition, you have to process the thing in the beginning, and when you're done with it, you go to the next one. So maybe you have 128 partitions, so you have 128 things that go in parallel. But if any one of them blocks on a particular partition, the next thing in line has to wait. Now, that's not entirely true, because you can fetch 1,000 at a time, but then hopefully within some period of time, you made progress on the 1,000 to get the next 1,000, right? And so head-of-line blocking is normally not a problem, but it's a huge problem for us, because if the thing in the beginning takes me 2 minutes to process, and all the ones afterwards would take me 1 millisecond, I wouldn't get to the 1 millisecond ones, because the one in the beginning holds me up. And you can simulate this out, and it turns out to just be really stupid. Because depending on like the variances that you have between them, you're going to spend most of the time just waiting, which is not great. So what do? We have a bunch of Kafka, which sends in a bunch of RabbitMQ. I showed this to others on a conference, and I was more or less laughed at for building something like this. But it's very pragmatic. It works. It uses Rabbit for what it's good at, which is fairly distributing work to all the people or all the workers that want to pick up work. And it uses Kafka for what it's very good at, which is buffering a whole bunch of stuff. It's not very clean, but it works. And it works for our problem in particular. And it turns out our problem is maybe a little bit unique, but not too unique. Because if you work with external systems, not every external system is going to be the same speed, right? And you don't control that system. And sometimes it's going to be faster, sometimes it's going to be slower. And so particularly when you do batch processing, the core problem is actually quite real. You just often don't notice how much time you actually spend not doing anything, just waiting. So I don't think it's a bad pattern. It just sounds a little bit like, I don't know, Fisher-Price solution of event processing. For Kafka, we had to learn a bunch because we also didn't know in the beginning how to do it. So we eventually built a reusable Python library that helps us a little bit with this and the different ways of doing this. There are some folks trying to port it to Rust now for our Rust pieces. But so far, this is a Python thing. Because it turns out that if you commit yourself to this idea of not doing work, you actually need to work to make that work. Because in Kafka, I'm picking up a thing in the beginning. OK, now I can throw it away if I don't want it. But if I want to have a chance of coming back later to clean up, I need to put it into a dead letter queue. It's not something that gives you out of the box. You have to build it yourself, right? There are different strategies of how you process this. Because, like, as we've mentioned, Kafka can only process one thing at a time, in a sense. So you have to find different ways in which you can work with these limitations. It's not a limitation. It's just an inherent part of how the system works. And it's surprisingly hard to do this. This is one of the other lessons that, again, in retrospect, seems very obvious, but takes a while to think of it this way, is that you have built the system, and it's a queue, and it basically processes events. Thing comes in, thing goes out. It has some natural properties of being in this stream that you can not just dislike, you can also leverage in a positive way. Very often when you build this queuing processing system like this, you hate all the limitations that it gives you. But it also has a really strong inherent property of it, which is all the things that are not taking place are not on your queue. All the things that are taking place are on the queue, right? And this is such an important property if you service something that's not always alive. So you have a certain number of customers. Not all customers are awake at the same time. Not all customers are sending data at the same time. Someone who is not sending data does not appear on the queue. This is obvious, but unless you take advantage of this, you can't build a system for it. So for instance, if you want to do something for every single customer at all times, run a cron job. Perfect. The only problem is that cron job is going to be slower and slower and slower the more customers you're going to have, because you have to do a thing for every customer. And it turns out for certain things that we want to do, the cron job was the wrong thing to do in the beginning. Because it actually turns out we only want to do it for customers that matter, only for customers that were there in the last 30 minutes. So we just put it into the queue. Like as a byproduct of the queue doing the thing that it does, it can do things on 4 customer accounts. So for instance, we have a system in place called dynamic sampling, which tries to intelligently optimize which data we keep, which data we throw away, which we have to recalculate in regular intervals. So for instance, if you always send the same health check transaction, eventually you don't want to pay for that anymore. So we're going to sample that one down. We're going to sample something else up. And so we don't want to run this calculation for every single customer account. We only run it for customer accounts that fall into certain patterns. And so we can put it into, as a byproduct of the queue doing stuff, we can recalculate things there. Again, it sounds really obvious, but it didn't come natural to how we were building this in the first place. Like grabbing, reaching for the cron is so easy and so obvious, and then you're just unhappy with how it performs. This is, I think, a very Sentry specific problem, but the shape of problem, I think, is common, which is certain types of processing requires a lot of data, and too much data to put it in the conventional caches. So Sentry uses a lot of memcache. I think a lot of people use a lot of memcache. It works really well for putting like small bits and pieces in there. For instance, server access tokens, session data, perfect to put into memcache. It turns into a problem when the cache that you need to have per customer is in the terabytes. And so at that point, you have to go to disk. There's no reasonable way around it. And this is sort of the problem that we have with Symbolication. When a native crash comes in, and you have to think of a native crash like this. There's an application, a desktop application. It misbehaves. It gives you like, do you want to send a crash report to the developer? User presses yes. It usually dumps a bunch of memory out and throws this memory to us. And then we have to make sense of the memory. We have to say, like, okay, so what did this memory mean? So we have to download the application. We have to download all the debug files of the application. For large desktop applications, for an individual crash, we need a couple gigabytes worth of debug files sitting around, right? So if we were to have to download them all the time, for every single crash report coming in, we would only spend the time downloading. So obviously, we need to throw it somewhere. But it actually turns out to be surprisingly hard to manage large disk caches because you have to keep them very close to where the code is running. And so we have this very stateful service that's basically attached to, I think, like I don't know how many terabytes large disk. But on average, on a day, it just keeps between, like, I think 6 and 10 terabytes worth of cache files around. And we memory map this into the process space, and we do a bunch of stuff in there. And this, again, is sort of there to fetch from the internet. And if the files that we get are just too slow, we have to tell the customer. Because if we didn't do this originally, we just pretended like we can do all the work we can do, and there was no reason for a customer to ever scale up their system to make us work better. And when you build a system like this, you can very easily build the same problem that we built, which is a fundamental flaw of building a system like this. So if you have these huge caches and you try to scale them to multiple machines, you end up in the beginning with like maybe 5 machines that all have this code running there, right? And each of them has like 2 terabytes worth of data of caches there. Now you put a 3rd one in there. Oh, sorry, I had 4 in the beginning. Okay, I put a 5th one in there. That one comes up with empty caches, right? That's how systems usually behave. Like they come up, empty cache. Not a problem. It should fill itself up really quickly. The only problem is your load balancer gives that service about the same weight as every other service. Now you can do this a little bit better. But even if you say, like, okay, I know that you're going to be really cold, it's going to take you much longer to respond to requests than anything else, I'm only going to give you 10% of the request rather than the 30% that you're going to be expected. It means that the throughput per service is still very different. So originally, my hot caches, they get 10 tasks a second in, and they produce on average 10 task results a second out. But the one that comes in cold is way slower. You put 10 in, and 2 come out, and eventually you have a backlog on that one. And as I guess queue theory, or whatever you call this, sort of tells you, is eventually everything is just going to go to the slow one, because that's just how the system naturally evolves. And there's actually there are lots of interesting ways in which you can solve this problem, particularly don't build it like this to begin with. But it's actually surprisingly easy to solve because you just share the caches. Like before you bring the service into rotation, you copy over the cache from somewhere else. It's going to take you a little bit because 7 terabytes worth of caches is not instant, but it avoids rewriting the entire service in a different way where you maybe have more active queues in it. And so this workaround that we made to this bad design actually turns out to be a permanent fix. Like we're like, okay, we're going to do it like this, and then we're going to solve it properly. We never had to solve it properly because that was good enough. Which brings me to my main learnings. Good enough is one of them, which is that when we built this originally, we didn't really know much about it. You have to think of it, it's an open source project that grew into a company, right? So it starts on the desire to run it with very little data for one person's hobby project. And then you go from there, and you're going to build it bigger, and you're going to build it into something that has to like service all of a sudden all the customers that are naturally flowing into the system. At no point in time do you have a lot of time to figure out how to build it better. Like there's no time when you can go back and say like, okay, now we have seen how this works, let's start from scratch. That just is not there. And so you pragmatically build yourself up and try to solve the problems as they come. But I took away some lessons that I think are universally applicable when you build processing systems. The biggest one is backpressure matters. And I didn't really understand how important backpressure is until I didn't put it into the system, because backpressure is this fundamental idea that it's not infinite. You have to tell someone you're full, either because you're going to load shedding, where you throw away extra stuff, or you just block and you hope that the person that talks to you will just pause. But you can't just eat up everything. It doesn't work. It makes for unhappy developers, it makes for unhappy user experience, it makes for high infrastructure costs. Nothing good ever comes from not having backpressure in a system. I wrote an article about this after my frustration of having built a system that doesn't have it. Because once you know that the people like me build a system without backpressure, you see it everywhere. The out-of-the-box experience in Python for async programming for many years was a write function that you didn't have to wait for. So you could blow, if you write fast enough into a socket in Python 3 on async IO older versions, you would just run out of memory, because it has an infinite buffer. There's nothing that says, like, hold on, I need to send it to the internet. It's just not there. It was forgotten about. So learn this lesson. Don't build a system without backpressure, because once you have done it, it's incredibly hard to get rid of. And then if you have this sort of backpressure management in your system, and some of this data comes from customers, you have to tell them that they are the source of something being slow. If you talk to their service and their service is slow, don't taper over it. Tell them that they have to scale it up, because it's going to make everything better. Killswitches are super important. We didn't have them originally, which meant that a bad customer data made into the event system, everybody was suffering. Now I can at least say, like, okay, you're the naughty person, I'm going to turn you off, I'm going to talk to you, trying to figure out why the data comes in. Or maybe it's my bug and I need to solve it. But being able to selectively turn off and on individual pieces throughout the infrastructure really quickly is very important, because once you have a backlog, you're not going to go to sleep, because you have to figure out how to burn it off. And you want to avoid backlogs at all points. The more control you can put into your pipeline to make rapid changes to it, like throwing away events or turning off the expensive part. When we make larger changes to an implementation of the pipeline, we usually keep the old and the new code in it, so that we can, like, if the new one doesn't behave like we want, we can route it quickly to the old one. It's very brittle. There's nothing complicated in it. It's really a very simple system. Like, we have not created something really complex or impressive, but just trying to chip away at the problems as they come. And so for me, one part here is, I mentioned this in the beginning, is that there's a very delicate boundary between a monolith and microservices. I don't know if we have found it, because you always find someone who complains that there's not enough services. But at the end, the only thing that really matters is that you deliver a reasonable service to your customer, and that you can deliver a reasonable developer experience to the people in the company. And somewhere in between, there is a reasonable balance. And that's why I will not advocate for either one of those things. It's somewhere in the middle. But yeah, for as long, I think, as you understand what the end result is that you want to accomplish, you will find a reasonable balance. But it's tricky. And specifically for if you have stuff that runs on the client, I think it's an important lesson to also measure what's going on there. Being able to measure, like, what the clients do, if they throw away stuff, if they're slow, if they're quick, and send this as core metrics into the rest of your observability infrastructure, gives you really valuable insights that before we had them, we didn't know that we wanted them. And with that, I think I have a little bit of time for questions.
Thank you very much, Armin.